Hello everyone and welcome to our calculus notes for section 4.6. Today we're talking about numerical integration. And so we're going to learn two other integration techniques, one called the trapezoidal rule and the other called Simpson's rule. And there are other ways of approximating definite integrals, especially of functions that are hard to find an elementary function that is the antiderivative of f. So let's take a look. In the trapezoidal rule, when we section off our intervals, so we'll just go from here to here. When we section off these intervals now, we can draw them here. As the name implies, instead of making rectangles like this, which is what we've been doing, okay, we're actually going to make trapezoids by connecting the heights of the two lines. And hopefully you can see that these trapezoids approximate the area under the curve a lot better than the rectangles had. So let me draw those rectangles in again. Okay, and hopefully you can see that the trapezoids are going to be a better representation than our rectangles. Okay, so what we need to do then is figure out, well, what is the area of a trapezoid? Well, the area of a trapezoid is 1/2 times base 1 plus base 2 times the height. So let's take a look at one of our trapezoids and figure out where all those things are. So if we look at this first trapezoid right here, I'm just going to call this our base 1, and I'm going to call this our base 2. And then our height is going to be right here. Okay, so it's kind of flipped on its side. So what we will need to do now is analyze this in terms of our function f of x and our x values down here on the bottom. So if we're going to go from our interval from a to b, alright, so we're going to go from a to b of our f of x dx. And we're going to approximate this here using these three trapezoids. So let's see if we can identify this. So this is going to be x sub 0. Here will be x sub 1. This will be x sub 2. And this will be x sub 3. So let's go ahead and find the area of this first trapezoid. And so it's going to be 1/2 times b sub 1, which in this case is our first height. And so this height is actually going to be f of x sub 0. Okay, so this actually becomes f of x sub 0. And then the second height here is going to be f of x sub 1. So it's the function evaluated at x sub 1. So here plus f of x sub 1. And then times the height, which now is the width of this rectangle, and it's also what we've been looking at in terms of delta x. So this width is like a delta x, and so really what we're going to do to find this height is we're going to take b minus a, or the width of our interval, and divide it by how many intervals we have. So in this case it would just be b minus a, and then it would be divided by our n intervals. Okay, in this case we chose 3, but we'll just leave it as n there. So this would give us the area of that first trapezoid. Okay, and then we would have to add it to the area of the second trapezoid. So let's find its area. It would be 1/2, okay, times its base 1, which is now f of x sub 1, plus its second base, which is going to be f of x sub 2. Okay, times the width of this trapezoid, which is still going to be the b minus a over n, because we separated this into n equal intervals. So b minus a over n. Okay, so that was our second one. And for our third one, so plus 1/2. Now b sub 1 is f of x sub 2. And this base right here is going to be f of x sub 3. Okay, and then all of this is going to be times our width of b minus a over n. Okay, so by adding up the area of these three rectangles, we're going to get an approximation of this definite integral. Now there are some things to look at here. We want to highlight in our function. So you can see here that all of these have a common factor of 1/2, and that's because it's just coming from the area of a trapezoid. So we could factor out that 1/2. Okay, what else does each of these areas have in common? Well, they all have in common the h, or the width of the interval, okay, because it doesn't change. So this b minus a over n is the same for each of these areas. So we're going to go ahead and factor that out as well. Okay, and then what we have in here is just kind of the difference of what's going on. And so if we were to look at this, I would have 1 f of x sub 0 and going down the line, now I have 2 f of x sub 1's. Okay, I have 2 f of x sub 2's. And going down left, I only have 1 f of x sub 3. That would be our last interval. And so this would be our approximation, 1/2 times b minus a over n times 1 f of x sub 0, 2 f of x sub 1, 2 f of x sub 2, and then 1 f of x sub 3, which is our last interval. So all of this is leading us into the trapezoidal rule. Okay, so the definite integral from a to b of f of x dx can be approximated by, well, it's exactly what we got here, b minus a over 2n, or 1/2 times the width of that rectangle. And then times, on the inside, f of x sub 0, notice there's only one of them, plus 2 f of x sub 1 plus 2 f of x sub 2, and this actually goes on and on and on, plus 2 f of x sub n minus 1, so the second to last interval, and then plus only 1 f of x sub n, which is our last interval. Okay, so notice the coefficient pattern here goes 1, 2, 2, 2, 2, 2, and then it ends with 1, and we can see how that worked right up here in our smaller example. So this here will give you an approximation of the area under the curve, or the definite integral of a function.